Okay, so we're going to be recording this part of the session. So if anybody has any objections with this, please say so now. Okay, so let's do a couple of more problems regarding forces on charged particles that have to do with magnetic fields. Now, this problem and the next one a little bit more, this one is gonna lead us into the next couple of topics that have to do with the Hall effect, Ampere's law, and a bunch of applications that have to do with magnetism, which is the real cool thing about magnetism and electromagnetism. And so what do we have here? We have a magnetic field, and the magnetic field is shown there with the little crosses. Can somebody tell me what the crosses mean in the magnetic field that were shown there? What do the crosses mean?
That
Anybody?
it's going directly at us or towards the paper, I remember.
If it's a cross, remember that it's like they're kind of trying to represent an arrow. So if it's a cross, it means that the arrow is going through the paper or through the screen. If it's a dot, it means it's going towards you. So right now, if it's a cross, it means it's going away, it's going into the paper, okay? And we've got a long wire. It's a 6 meter long wire, okay? The wire is 6 meters long, and it's carrying the current of 120 amps, okay? And we put that wire within the magnetic field. And so just remember something that's very interesting about magnetic fields. Imagine that magnetic fields, it's kind of like being in I like to think of it this way. It's kind of like being in a river where there's a flow, or maybe rather than a river, it's kind of like being maybe in a world, in a sort of like let's imagine like a jacuzzi or something like that, where there's fluid and it's moving around. That's the magnetic field. And then we put something within that fluid movement, and that something creates an effect. And this effect is a force. So this kind of happens. There's a magnetic field going towards the page, and then we grab a wire that's carrying 120 amps, and we put it in the magnetic field. What's going to happen? If we remember, this is the rule. This is what we're talking about in the whole unit. There's magnetism, there's magnetic fields. If we put charges that are moving in a magnetic field, a force is, I'm sorry, a force is going to be generated. Sorry about that. A force is going to be generated. If it's one charge moving through the magnetic field, there's going to be a force on that charge. But if it's many charges, which actually is a current, so a current isn't anything else than many charges moving through a conductor, then there's a force that's also going to be exerted. Now, the important thing here is that the uniform magnetic field is 0.2 Teslas, and the magnetic field has a width of 3.5 meters. So the cable, the wire is 6 meters long, but the magnetic field is only acting in a space of 3.5 meters. And we want to determine the magnetic force on the wire. Okay, we want to know the magnetic force that's being generated on the wire. I'm going to go through it, and please, if you have any questions, let me know. So first off, let's try to identify the direction of the force. So what I'm going to ask you to do right now in your spaces there is to try to use your right-hand rule, and try to determine where the force is going. Let's just remember this. We're actually talking about the second right-hand rule because we've got a current. So the current would be your finger. Then the magnetic field would be your index finger. The magnetic field would be the rest of your fingers, and the force would be your thumb. Okay. And so try to do that with this one. Okay. Try to kind of visualize where the force would be going. Okay. So let's do that. I'm putting my hand here in the diagram or in the image. Try to do that with your right hand. The fingers are going into the index finger is going to be pointing. I'm not sure if my video is mirrored or not. Let me just check this. Yes, it is mirrored. So it's confusing for everybody. That's why I put the image there. The magnetic field is going into the page. That's why these fingers are going into the page. The current is going this way. That's what this is indicating. The magnetic field is going into the page. That's why these fingers are going this way. And so the force that would be exerted would be that of the thumb that's going this way. And that's what's being indicated here. There's a force that's going through the field there. Give me a moment. Okay. And so there's a force going to be exerted. Now we know that according to what we've seen before, the force, the force that's going to be created according to the magnetic field is going to be influenced by the moving charges, which in this case is the current, and the space they're moving through, which is the length in this case of the cable. The magnetic field also, and the magnetic field that's perpendicular to the current. In this case, the current is going this way, the magnetic field is going directly into the page, so the angle that forms between the current and the magnetic field is 90 degrees. The current is 120 amps, and the length where the magnetic field is acting is the width of the magnetic field. So regardless of if the wire is 6 meters long, the magnetic field is only acting on the 3.5 meters where it's located. So the force is going to be equal to 120 amps times 3.5 meters times 0.2 Tesla times the sine of 90 degrees, which is the angle between them. So the total magnetic force that's experienced is 84 newtons. That's a strong force. Why is it a strong force? Because we've got a strong current. We've got a strong current. 120 amps is a strong current. 0.2 Teslas is a relatively medium, maybe sized magnetic field. Remember, a 1 Tesla magnetic field is huge. And so we've got 84 newtons. And the force would be going up. Okay. Questions with this one? Again, it's just kind of applying the right-hand rule and the principles of the force. Remember, when we were talking about charged particles and electrical force, the force was going to be proportional to the electrical field times the charge, or it's going to be proportional to the charges and inversely proportional to the square of the distance. Here, the influences have to do with the charges that are moving, the space they're moving in, and the magnetic field strength perpendicular to the movement of the charges. Okay. And so this is important because, again, there are forces that are interacting here. So whenever I have a magnetic field and then I put moving charges in the magnetic field, forces are going to be generated. And that principle of magnetic field combined with moving charges generates forces can be used in many ways. I can also have a current that's going through a cable, and that current is also going to generate a magnetic field. If I have movement within the magnetic field of the current that's moving, or I move the magnetic field, that's also going to generate an effect. So this has many, many, many applications that we're going to talk about in a moment. Okay. Questions with this problem? No? Okay. Let's see another one. Another problem. Okay, let's see another one. I never thought adding pictures of my hand would be useful. Again, if we were face to face, it'd be different because how we would be seeing each other. but these pictures of my hand are going to provide useful for a few other things. Now let's think about another problem. Now we've got a charged particle. It's a plus 55 microcoulomb charge. Let's assume that that charge has a mass. It has a very, very small mass. And it's moving at a speed of, it has a mass of 0.013 kilograms and has a speed of 15,000 meters per second. So again, it's a charge. We're going to consider that it has a mass for the purpose of the problem, and it's moving very fast. And we kind of take a snapshot of that. It's moving through a magnetic field. And we're considering that that magnetic field close to the Earth is 0.125 Teslas. Now, we're also going to consider that there's an electrical field. That's 2,500 newtons per coulomb. Now, it says, draw a free body diagram showing all three forces that are acting on the charged particle. Can somebody tell me the three forces that are acting on the charged particle? What are those three forces? Anybody? There's three forces that are acting on this particle that's moving through the magnetic field and electrical fields. What are these three forces? Can somebody tell me? Anybody? What's the name of this unit? What's the topic? What's one of the forces that's acting on the charge? Come on, the magnetic force. Perfect, got it. That's one of them. The magnetic force is one. So we're going to have a force. The three forces is we're going to have a magnetic force. I'm going to call this FB, the magnetic force. Horrible writing. Horrible writing. What's the other force that's acting? One is the magnetic force. What's the other one? Anybody? Come on, show me that you're awake.
Electric field.
We've got an electrical field, so it has, there's also an electrical force. I'm going to call that FQ. That this is regarding the electrical field. That's the second force. What's the, just give me a moment here. I just want to do this. I'm a sucker for colors, color coding. Let's write this one in. There's a FQ, I'm going to call it, which is the electrical force. And what's the third force that's acting? We've got the magnetic, the electric, because we've got the electrical fields. What's the third force that's acting there? That has to do with the information we're being provided. Come on, anybody?
Isn't it the,
Could you say that again, Omar, please?
the charge of the particle?
Well, that has to do with the electric force. So the charge, so I'm just going to color code this. So the charge and the electrical field are the electric force. And the charge and the speed and the magnetic field, that's the magnetic force. What's the third force that's acting there?
Is it gravity?
It's gravity, correct, correct. We are considering that the charge has a weight. So there's also I'm going to call this Fm, mass. There is gravitational. Just going to write it as grav. So there's three forces acting in the particle in different directions, and we kind of want to know what the resultant effect of all of these forces is going to have on the charge. Is this clear to everybody? Questions before we move on? Let's look at how those forces interact. Erase this and move on. So first off, let's kind of see where the forces lie. So first off, we are going to have, we're going to use the right-hand rule. The magnetic field has little dots on it. That means that it's going towards you. The V, or the red line, is going to be the vector of velocity of the force, of the charge, I'm sorry. And so the thumb is going to indicate the direction of the magnetic force. So we've got the forces here indicated. The color coding is different actually from the ones they're using over there. No, actually it's the same. It's the same. It's the same colors. Green is going to indicate the magnetic force. It's going this way. It's going in the direction of the thumb. It's going in the direction of the thumb. And it's this force that's going here, the magnetic force. They're calling it FM here. Then we're going to have another force that's going directly down, which is the weight, or the gravitational force. And then we've got a electrical field force that we're going to put it going this way. And the problem states that the particle that's moving with the velocity, which is this red arrow here, has an angle of 40 degrees with the electrical field. Okay. And so that's this 40 degrees that we've got here. And using Pythagoras, this is 90 degrees. And so if this is 40 and this is 90, this has to be 50 degrees. And so we've got the free body diagram of the three forces. Now, each of the forces has a magnitude that we can calculate. So the force regarding the magnetic field is going to be the force relating to the movement of the charge and the magnetic field. The force regarding the electrical field is going to be the charge multiplied by the electrical field. And we know that the force, or the gravitational force, it's going to be mass times gravity. And so with that information, we can do the calculations. The Coulomb force, or the electrical field force, this is the blue, this is the electrical, is the magnitude. The magnitude is going to be Q times E. So the electrical charge times the coulombs, we've got 0.1375 newtons. The magnetic force, which is this one, is going to be, as we've seen in the previous problems, the charge times the velocity. The charge times the velocity times the magnetic field times the angle, and it's going to be 90 degrees because it's going through the page and it's going to be perpendicular. So this gives us 0.103125. And lastly, we are going to have the gravitational force. Gravity. And this is going to be the mass times gravity, 0.013 times 9.81 meters per second. We've got 0.12753. That's going to be the magnitude of the forces, but we need to calculate the resultant force that combines all of these effects. And so using the free body diagram, we calculate the forces in X. So we're going to consider that the left-hand side is negative, right-hand side is positive, up is positive, and down is negative. So if we do the forces in X, the force that has to do with the electrical charge is going to be negative, and it's along the X axis. The force relating to the weight is going to be 0. There's no X component. And the magnetic force in X is going to be the magnitude of the magnetic force we calculated times the cosine of 50. That gives us this number. And when we add all of this up, we get minus 0.07121. Now, if we go to Y, the force regarding the electrical field in Y is going to be 0 because it's along the X axis. The weight in Y is going to be the magnitude we calculated, but it's going to be negative because it's going down. And the component in Y of the magnetic force is going to be the magnetic force times the sine of that we had already calculated times the sine of 50. By the way, remember that the free body diagram, we can really align it however we want. We're aligning it so the electrical field and the force and the weight are perpendicular to each other and aligned to the X and Y axis. That way we don't have to do many calculations with angles. And so we've got the resultant X force and the resultant Y force. And after that, the only thing we do is apply Pythagoras to calculate the net force, which is going to be 0.8618, and the angle is going to be calculated with the relationship, the inverse tangent of the relationship of Y and X. That's going to be 34.3. With regards to X, so the net force is going to be 0.086 at 214.3. Why 214.3? Because the angle we're given is always going to be the angle with regards to X. So this angle here is a 35.3, but if we want the complete angle that goes from here to here, then it's going to be this angle plus 180. And that gives us this angle here. If we divide that force times the mass, we're going to get that it's moving to get the total acceleration. We're going to get that the total acceleration of the particle is 6.63 meters per second. So the forces are at that point, at that moment, the charge is moving at 15,000 meters per second, and it's going to have an acceleration of 6.63 meters per second squared due to the combined effect. This is going to be the effect of the charge with all of the three forces involved. Okay. Questions with this problem before we move on to the next? No? Okay.